and get started. Okay.
Okay.
So
We introduce you tonight, just because you're that special. So today, we're very grateful to be able to hear from Dr. IQ of Loyola University of Chicago. And she's going to be delivering a talk on time-resolved leader spectra of downward terrestrial gamma ray flashes observed in the telescope array surface detector, and the first downward TGF observed in association with dark leaders. So I think we're all really excited to hear what she has to say.
okay. Thank you so much, Jeffrey. So today I'm going to show you the observation of downward TGF at the telescope array surface detector. So okay, so the main thing of this talk today is I want to show you our recent observation of downward TGF at the telescope array surface detector. So the first result is the optical observation of two downward TGF. We observed in 2023 a low peak current event and a high peak current event. And another result is the downward TGF we observe in association with dark leader. So this is the result we observe in 2024. And the other is the introduction and the setup experiment at the telescope array surface detector. So for the introduction about TGF, we're quite familiar with TGF. So basically they are just energetic gamma bursts. And one of the reason we still need to observe and study on TGF because we really don't know the real mechanism that produce TGF. Lightning can produce TGF because the number of photon at the source is very high. And so this is a short introduction of TGF and the experiment set up. So we are TASD team, so which is the telescope array surface detector. So the TASD is quite big, quite large telescope at the north part of the US because it includes 507 scintillator detectors and is cover an area of 700 kilometers. So the TASD detect whether that source could be a TGF or not. And in the area of 700 kilometers here, so we have other lightning detector that can cover the entire area, so which includes a fast antenna, two fast antenna, which is the fast electric field chain, and lightning 11 lightning mapping array, so which is 11 blue dot here, and then national lightning network detection. So this we combine, we collaborate with a company to get information, the lightning information, and then we have two other interferometer waveform here. And they are lightning detector. And about the optical observation, we have a high-speed camera here and a spectroscopic system which include a camera and a prism in front of it. So the spectroscopic system were installed here at the same location with the interferometer, with one interferometer and one fast antenna, and then the field of view of the two optical observation can cover some like most of the ASD area. And now is the result that we observe. So in 2023, we observed 7 events, but in that 7 event in this area, we have only 2 best event. So the first TGF observed at this location in front of the camera, which is 16 kilometers away from the camera, and we observe only one. We name it single trigger, so we observe only pulse like this. And then The second event we observed with high peak current minus 33.4 kiloampere and is around 20 kilometers away from the camera with 2 triggers. So now we go to the first result. So the first TGF is here, and so the fast antenna, the green color is the signal from the fast antenna. So which show us this is the initial breakdown pushes of the stroke, and then the step leader, and then the return stroke here. And then the TGF were observed during this time, and then this is the spectroscopic data from the spectroscopic system, and this is the luminosity event here, the luminosity loss from the high-speed camera. So what we see in this TGF is that we see the TGF were observed during the IBB stage of the stroke, and it's quite similar to most of the TGF we observed, the TASD. And then when we zoom in this area here, so we see this is the IPP, the IPP signal here, and then spectroscopic data, and then this is the spectroscopic data around the TGF detection. So now we zoom in this area to see what is mean of this icon. So in this area with the TGF here, and then this is the spectroscopic data that we observe. So now here is the image of the spectroscopic system here. So the first one is not inside the H here. The first one is this, is corresponding to the strongest IPP here. So we see the optical signal, but I give you the gray color here because the gray icon here. Oh, sorry, this is the gray icon, not blue. So the gray icon here, because we see the optical data, but we did not see any emission lines. We see the continuous spectra here, but I remove the continuous spectra. And after that, so close to the 8 frame close to the TGF, so we see the ion emission here in the blue color, and then a neutral emission here. So the spectra with ion and neutral emission, I name it the ion emission. So it's included the neutral and ion emission. And then other spectra, we see only the neutral emission here on the bright part. And then at the moment we have the TGFs, we have only neutral emission here. And then after the TGF emission, we see ion emission again. So so for conclusion, so what we observe here, the result here is quite similar to the result in the paper that we just published in 2024. So we see the ion emission before the TGF, and then it disappear. And then after TGF, we see ion emission again. So that's we name it the appearance and reappearance before and after TGF detection of ions. But it's always that right at the moment we have TGF, we see only neutral emission, no ion emission here. And the new thing for this event this year is that we have the high-speed camera record the event simultaneously with the spectroscopic. And here's are the images that we record. I select to show here is before the TGF. So there are 10 images here. So there is corresponding to this position. So the first image is corresponding to this IPP with image B, no IBB, C corresponding IBB, and D corresponding IBB, F and H. So compare here. So you see the H with IPP here. The image is quite blur, so we don't see a clear channel. It looks like a light ball here. Image H, image C, image D with IBB, image F, image H here, where we have the TGF. So this means that the high-speed camera image show us one thing that with the IPP, we see the saturation. We cannot see clear channel. We see the saturation of the channel, and without IPP, so we can see the clear shape of the channel here. And this is the entire stroke of the channel. So the first conclusion for this event is that it's quite similar to the, it's consistent with what we have been observed in the past. And the TGF were, because the TGF was produced during the initial breakdown process, we see the ion appearance and reappearance. We see the neutral appear at the moment we have TGF. And then the new thing is that we see the corresponding between IBB image and the image without IPP. So this is important because it's related to the second TGF here. Now we move to the second TGF, which is 21 kilometer, 21, not 20 kilometer in front of the camera here, and high peak current. So this is a waveform of the IPP, of the electric waveform of the stroke related to this TGF. So the first thing we notice is that this waveform is unusual behavior, because we don't see a strong IPP when the TGF was reduced. And we also don't see the clear distinction between the IPP process and the step leader and then the return stroke. That's the reason we name it unusual. And then when we when we check the duration of the IPP from the initiation of the flash here at this point to the when the recharge happened, so it's happened quite in a short period, only 1.2 millisecond, and no distinguish between IPP and TGF. So this is the first unusual thing. And the second thing is that we see these are the spectroscopic emissions. So gray color means that we have the optical signal, but we don't have we don't have any spectral light. And then we have ion emission. We have neutral and ion emission, and then neutral and ions. And after TGF detection, we continue seeing ion emission in a long periods. Until the stroke hit the ground. So this is quite weird, because for the first TGF, we do not see anything after TGF detection, right? And then the return stroke. And then another weird thing is the luminosity plot. The luminosity plot of this. So we see that around the TGF detection here, usually for the 6 TGF we observe in 2021 at the TASD, we see the luminosity plot will peak as the moment that we have TGF. Is similar like the here. Luminosity will peak at the moment we have TGF, and then nothing, and then the return stroke. But in this case, we see that the luminosity does not peak here. It's just a little bit here, and then it keep increasing until it's reached the ground. So these are the unusual thing of the second TGF, the second stroke that reduce TGF. So now when we go into the spectroscopic data of this event, so we zoom in this area. So we see that it's interesting that we also see the ion emission before the TGF, and then we have the neutral emission. And then at the moment we have the first burst of TGF, we have neutral emission, and then ion re-emission, re-emission. The moment we have TGF, so we have only neutral and then ion re-emission. So it's quite interesting that even there are some unusual about this TGF, we still see the behavior of the ion appearance and reappearance before and after TGF detection. And at the moment we have TGF, so we have only neutral emission. And for about the high-speed camera image of this stroke is that we do not see the saturation, which is a light both that's similar to the first TGF here. So it's quite weird for us. And then, so we explained the reason we don't see it because we did not have strong IBB. So that's the reason we don't have the saturation of the TGF. And some people, they argue that, oh, it could be because of the attenuation, the rain condition of the cloud, something. Yes, that could be one of the reasons. But normally as a TASD, with this high peak current, more than 100 kiloampere, normally we cannot record the clear signal because the system only gets saturated. But for this case, we don't have. And so this is the conclusion of this TGF, is that it's consistent in the sense of the ion and neutron emission in the spectroscopic observation, but there's some unusual because there's no strong IBB. The way the electron waveform change is unusual, and the ion emissions was dominant in the spectroscopic. We have the luminosity plus the not peak around the TGF and the optical image without saturation. So because of this unusual behavior, so we have to work for that. And then I found a paper in Japan from this group where they study a lot of high energetic TGF, and one of high energetic lightning event, sorry, not TGF. So in this paper, they show the waveform, more than 10 waveform of they name it the strong negative return stroke, and it's quite similar to our waveform. So the reason this stroke quite special because when they study with the stroke with high peak current more than 115 kiloampere, and their duration is less than 700 microseconds, and our stroke, we think that is, they name it special strong return stroke. It's special because it's not similar with normal return stroke. And in our case, we also see that, and we cannot conclude now, but we think that the TGF the stroke that we observe related to the TGF2 is could be belong to this category. It's special, so that's the reason we see some weird behavior of it. So that the event in 2023, and for the event in 2000, so that's these two events. We published the paper. Well, no, we just submit the paper recently, and hopefully that we hear back from the journal soon. And now this is another event we observed in 2024 related to the dark leader. So this is, we're going to submit another result soon. So this is the first time we observe TGF associated with dark leader events. So to remind you a little bit, what is the dark leaders? So before we have return stroke when the return stroke hits the ground. So before that, we have the development of the channel, which we name the step leader. We name it the step leader. If we name it the step leader, so it's the leader before the first return stroke here. And then when the stroke hits the ground, and the stroke will stay for some time, and then it stops, and then in the same path, so we will have the dark leader that develop in the same path. And then after some time, when it's connected with the ground, so we have the second return stroke, and then the stroke disappear, and then we have another dark leader, we have the third return stroke, blah blah blah. So what's it mean that a lightning flash will include one or several return strokes, and the leader that go before the first stroke we name is step leaders, and the leader that go before other subsequent strokes we name it the dark leaders. So until now, for the moment, so all of the TGF, downward TGF we observe at the TASD were detected during the step leader stage there, and not only at the TASD, as far as my knowledge, so there are no any TGF were observed during the dark leader event. So we are the first time, so we are the first group that observed the dark leader, the TGF related to the dark leader events. So the events will happen in August 17, 2024. So it's happened with an unusual storm that on that day, because we observe 9 TGF within 30 minutes on the ground. So this is the highest TGF observation rate that ever recorded at the TASD. So we can compare this rate with the I love campaigns, but later. So you see, like we observe in every few minutes here. So 9 event, and among of them, so the event we observe at 16 o'clock 18 minutes 45 seconds, so which is the dark leader event. So the events were observed right at the edge of the field of view of the camera. So the two camera here and the field of view of the high speed camera like this, and it will observe right at the edge of these two camera, and this is the energy observed from the TASD data, and we check with the LMA data and lightning network, like the network, national lightning detection network here, and this is the waveform that we observe. So now we check whether we sure that this is a dark leader event, because the TGF we observed at 16 1845 here is related to this stroke 76 kiloampere, and then when we check back, so at 16 1844 here we have other two stroke with different speed current and in the same location here, but then we are not sure whether it's does they where we are not sure whether they are 3 subsequent stroke in the same flash. So now we continue to check the spectroscopic image here. So why do we check the spectroscopic image, not the high-speed camera? Because the event right at the edge of the high-speed camera, so the high-speed camera was not able to record it. So the reason we are able to see is because of the algorithm in front of the spectroscopic system, which bent the direction of the light. So therefore, for this event, only the spectroscopic system were able to record it. And then we check the shape of the first stroke, the second stroke, and the third stroke, and they are in the same shape. So then we show that so they are in the same strokes they are different stroke in the same flash. And now when the fast understand, now we check the data here. This is the stroke, first stroke, the second stroke here, and then the third stroke. The TGF was recorded very close to this event here. And then when we zoom in this event, so this is the waveform of the first stroke here, and this is the image of this. So this is the time, the black point is where we have is the time where we have the where we record the spectroscopic image here. This is the first stroke. This is the second stroke, the image, the camera image here. This is the third stroke, the camera image here, and the TGF will record it here. So now we go to the characterization. We come back to remind a little bit. So if you pay attention, you see that this stroke, the first stroke, we don't see the initiation of the stroke. We don't know the duration. The second stroke, then no thing. So it starts from here. And then the third stroke is start from here. So this is the 3 strokes. And then now we characterize the TGF. So we see that we use the interferometer data, the LMA data, like the network detection data, and the ASD data. We match all of them together. We do the time shifting for different locations. We do similar like what we have learned before. So then we come to conclude that so the TGF will produce only 1.4 kilometer above the ground which is very, very close to the ground. The duration is 55 microseconds. The maximum energy deposit is medium maximum. The fluence belong to the low fluence TGF, and the velocity to close to 3 × 10⁷ microseconds. So this is very high speed, because very high speed of photon. Here, this is the waveform of TGF. This is the initiation of the third stroke here. Okay. And what is the unusual about this TGF? Because it records a very low altitude, and it's very close to the return stroke. And all this TGF will have all the 3 return stroke of this flash is happen in the very short duration. So the reason why we pay attention to the close to the return stroke, because for most of the TGF we observe at the TASD, most of the downward TGF observed at the TASD, most of them were observed during the initial breakdown pushes, not anything close to the return stroke. And now, so we just try to summarize. This is the conclusion. So the unusual thing of this lightning flash is unusual because it already happened during the unusual storm on that day with very high TGF observation rate. The first stroke, we don't know the duration of the development of the stroke. The second is that we assume this is the initial of the stroke, so it's happened in 275 micro duration. And the third stroke is 281 micro duration here. So normally we never observe any stroke with this short, because we observe stroke, like you see, for the unusual event I just report. So it's the shortest one is 1.2 millisecond. And now all of this event we observe less than 300 microsecond. It's special stroke, special flash, and then we have special event because it's related to dark leader. And for all of this, so what we could think of is that maybe the speech of, so this means, I mean, after all of this event, we see TGF happen before and after the initiation, and then the last stage of the leaders. Then we think that the leader speech could be one of the main factors that contribute to the reduction of the TGF. So with this, so I think these are the conclusion is similar to what I talk here. Yeah, so I finished my talk.
Thank you very much, Nai.
Sorry, too fast.
Don't worry. Does anybody have any questions or discussions they'd like to bring up?
Yeah.
Okay.
Yeah, hi, Melody.
Yeah, I can have a question.
Yes.
Maybe I don't know if you have an answer, but it would be great to have your point of view on this.
Yes.
Do you think that there are differences between upward and downward TGFs?
Yes. Yes.
And which one?
So it's, I mean, that in for this TGF, the high this current event here, there's different, because so I mean, this at the beginning I was confused, and then when I studied carefully, I realized that, so there are some paper they already speak about this. So we have the energetics EIP, so which is the energetics in cloud pushes. So that's kind of stroke. That's kind of a stroke. So they are intercloud strokes. So if the negative EIP, so it's related to downward TGF, and the positive is related to the upward TGF. So I mean, that if we understand the polarity of the event, right, you see that why this event create upward TGF and another event create downward TGF. That's the first thing. The second thing is why I mentioned that, because the waveform of this stroke, this is the down, this is the cloud to ground stroke, but the waveform of this special stroke is similar to the waveform of the energetic intercloud push. So it means that this is the, what I mean is that this is the cloud to ground stroke, but the waveform is similar to the events of the intercloud stroke, and that's the reason we are able to record this event. So there's some difference between, and this kind of stroke is similar to the, and oh sorry, I forget to mention, in this paper, the Japanese guy, this guy, he said that this in his paper he didn't measure any TGF, but he said that this kind of stroke may produce the downward TGF, and that's what we observe. So
There's a reason he made that statement, Nai.
yeah, really.
That particular stroke that you have, well, one of these, I think it's the very bottom one. I'm not sure, I can't quite recall, but it
Right.
was coincident with the TGF. The reason he
What?
made that statement in the
Oh,
paper is because the UCSC group Thor observed a TGF, got the information of what lightning stroke it was associated with, and then happened to run across Ting's paper. And so then reached out to Ting, because Ting published in this paper the exact same spheric that was associated with the TGF. So there is some really interesting relationships that are sort of in play here on these compact return strokes and TGF observations. So there is a connection between the two.
yeah.
But essentially, Ting's paper here talked about how these compact return strokes, what was the interesting part of the paper is that he showed the evolution of how a normal return stroke sort of evolves into this compact structure as you shorten the leader length. As the leader
Yes.
length gets shorter and shorter and shorter, this sort of characteristic waveform starts to take shape. And so it's really just sort of a scale, of the longer the leader, the more traditional the waveform looks. As the leader gets more and more compact, you get this interesting sort of waveform look with this compact return stroke look to it, right? So it's very Ting's work is very interesting.
Yeah, thank you. Yeah, yes, that's the reason I say that the speed of the leader could be one of the main thing that produce TGF, because when you shorten the leader, right, development, it means that the leader have to move very fast.
Yes, the
Yeah.
speed.
Yeah,
Yeah.
the speech. Yeah, so yeah, that's the reason. But yeah, you're right. In this paper, I didn't know why he has that statement, but we saw that. So, and this is our confirmation for him, but not sure 100%. So that's the reason I need to ask. Nice. I
I have a question.
thank you.
And I think this is with everything, all the interesting observations that are
Yeah,
made at the large array here
yeah,
with the Aloft campaign, right? I think we're noticing a very strong blurring of lines between what is a TGF, what are step leader X-rays, right? Is there,
yeah,
a few years ago,
yeah,
we put them into very separate camps, right?
yeah,
Step leader X-rays were one
yeah,
thing, TGFs were another, and we tried to sort of, separate, that step leader X-rays were not RIA, they were low energy, they were very, very, very short in time scale,
yeah.
right? TGFs had a RIA spectrum, they're harder in harder in emission, they're longer in time scale, right? So now that's kind of blurring a little bit,
Oh, okay.
right? So like, for instance, the first two events that you were showing,
Yeah.
right?
Yes, yes, yes.
They're happening at the initial breakdown pulses.
Mhm.
They seem to be, just looking at your time scales, they seem to be very
Yeah.
short in duration.
Yes, this
Right? But
this
what,
one, no, no, this is the energetic, this is the darkly the events, right?
yes,
Yeah,
no,
so
not the dark, the very beginning, like
the very, yeah. Not this
you know,
one.
event 1 and 2,
Yeah, this is
you know,
event
like
two.
that one and then the one before it.
Yeah, the one before is longer. This one is normal, is longer.
Yeah, that little, just the little mission, the purple line there. How long is that? How long is the actual TG?
So this one is around 40 microsecond.
40 microseconds?
Yeah.
Okay, gotcha. Right. So,
Mm.
yeah, so yeah, and then the other ones were a little shorter,
The other one is longer because
longer.
yeah,
Okay,
50. This one, yeah, a little bit longer. Look at it away from here. Yeah.
gotcha. Each
So,
individual one is like 50 microseconds.
I think it's no, it's the sum. It's not. It's individual one. So it's the sum of all of the detector that we have. Like many detector here, right?
Yes.
Yeah. So with some like 4, 5, like some the main detector. So the one that detect that very low energy. So we remove them. It's some
Gotcha.
little. I forget
I,
to
I,
show
I
you.
see. I see what you're saying. Yeah. So
Mm.
I just think it's an interesting thing because that
Mm.
line does kind of blur,
Yeah.
right?
Yeah. You're right.
Between, you know, what is, see these sort of, you know, like very, you know, like the traditional, very large, very high luminosity, very, you know, distinctly TGF and then, you know, step leader progression,
Yeah.
X-ray emission. So
Thank you
it'll be
so much.
interesting to see if you were able, you know, if you publish this, if you're able to put in, you know, look at the energy spectrum and see if it aligns with, you know, a RIA spectrum and that kind of thing.
Yeah.
So
Thank you so much. Thank you so much for the comment of the blurring, the blurring between the X-ray and the gamma ray. So
it
that's
does.
what we want.
Yeah, I don't think we can, at this point in where things are, I don't think we can really, things are just a little too muddled and gray right now.
Yeah.
To try to, you know, as the sort of zoology of X-ray emission or, you know, of radiation from thunderstorms is getting a little muddled.
Yeah.
There's just too many new observations and too many unique things happening for us to be like, this is this and this is that.
Yes.
Right.
Yes. It's true. Yeah. It's
Yeah.
nice. We love it. And so I mean that we already for the dark this paper we already submit, but for the dark leader we try to submit it soon. So we have finished everything. Now we just need the introduction. That's what you just said. What you just introduction for the paper and then the discussion. Yeah.
Yes. Yeah. So yeah, feel free to quote me. Muddled.
Yeah. Thank you.
No worries.
Thank you so much. Then
All
okay.
right. Any other questions?
Is this answer your question, Melody?
Yeah. Thank you.
Thank you.
It was super nice, your talk.
Thank you. Yeah, I want to ask people opinion about this because it's quite new to us. Yeah.
Well, I really appreciated your talk. It was very interesting.
Thank you so much.
Yes. So I'm looking forward to the paper coming out.
Yeah, thank you.
Okay. Well, thank you, everybody. We'll hopefully see a handful of here that showed up next month. You'll get emails about who our next speaker is and all of that. So,
Okay.
okay.
Thank you.
Thank
Have
you.
a good morning.
Thank
Bye
you.
now.
Have a good bye.
Have a
Bye-bye.
good day.
Thank you. Bye bye.